So, welcome everyone to this talk called The Productivity Trap, where we're going to talk about the perils and promises of AI-assisted coding. And this is a broad topic, and I want to make sure that we cover both the good, the bad, as well as the slightly ugly side of AI. So let's start with the promises. Let's start what's being sold to us. So I think we have all seen this claim that adopting AI will make us 55% faster on coding. And the first time I saw this claim, I got really curious. What is it based on? How can we know that we become 55% faster? And it turns out it's based on a research paper from people at Copilot. And it's a pretty good research paper because, like all good research, it's very clear about its limitations. And I want to walk you through some of these limitations. So you don't have to read the whole wall of text here. I'm going to walk you through the key findings. So first of all, the effect seems real. Indeed, participants in this study became 55% faster at certain coding tasks. However, the research is also very clear that there's no guarantee whatsoever that these findings generalize to programming in another context, right? What the study also points out is that the less experienced developers, more junior developers, they were the ones that benefited the most. They were the ones that got 55% faster. For more senior people, the benefits seems lower. But the thing that really caught my attention was the last point here. This study does not examine the effects of AI on code quality. And for someone that has spent 15 years working on code quality tools, this really, really worries me. And I was worried for a long time until finally, at the end of last year, there was another study published. And this study promised to look at AI from a code quality perspective. And it's a very interesting study. It's a large-scale study, and this time it's done in a real production setting, studying thousands of engineers at work with AI. And the findings from this study reports that, yeah, we didn't become 55% faster, but we got 26% faster on task completions. So that's okay, not 55%, but 26%, that's still a significant speed up. So that's interesting. But again, what caught my eye was point number 4 here, that quality was maintained. There were no adverse effects on code quality whatsoever observed in this study. And I thought, wonderful. It seems like we have our first free lunch. We can become significantly faster without sacrificing quality. Isn't that beautiful? It was to me, at least until I started to look at how did they measure code quality. Do you know what they used to measure code quality? They used the build success rate. And let me be very clear about this. Measuring build success rate, there's nothing wrong with it. It's fact, it's excellent if you want to know about build success rates. However, a build success rate is a very, very low bar for measuring code quality, right? The thing compiles or not, it doesn't really tell us much, right? Rather, code quality is about the longevity of the system, right? Can the code be maintained, understood, and changed as the business need changes? And a build success rate simply cannot capture that. So we seem to still be in a space where this year and next year, we will see more code than ever before. Because remember, writing new code is faster than ever before using AI. But there's a big unknown for quality. We simply don't know what the quality of all that excess code that we generate will be. And this makes me question if we are focusing AI on the right problem. Because current AI tools focus on helping us write more code faster. And if we look at this graph, which explains where we developers spend our work week, we see that writing new code is a very, very small part of where we spend our time, roughly 5%. And still, those 5% is where we are focusing today's productivity tool. And let me translate these findings to you, to what they actually mean and imply. So becoming 55% faster on writing new code translates into roughly 1 hour saved per work week. So 1 hour is 1 hour, right? Nothing wrong with that, but it's not that groundbreaking. Instead, we see that the big win is in helping us understand existing code. That's where we spend roughly 70% of our work week, right? Trying to understand what the system does so that we can implement the next feature or fix a bug or whatever we're aiming to do. So the takeaway for me here is that if we want to improve any aspect of software development, we should optimize for ease of understanding. That's clearly where the big win is. And if we do that, then there's no need to settle for just 55% faster. I think that bar is way too low. We can actually get 10x faster at what we do. And yes, I know, 10x faster, that sounds like a absolutely ridiculous claim. So I'm very, very happy that I have some data to support that statement. So please have a look at this graph. This graph comes from a research paper that me and my colleague, Dr. Marcus Borg, did a couple of years ago. So what we did here was that we looked at code quality using a metric called code health. I'm going to talk a bit more about that later. But basically, code health categorizes every single piece of code as being in one of 3 different categories. So you can either have green healthy code that's easy to understand, and then you have increasing levels of technical debt and code quality problems. And what you see in that graph is on the y-axis, you have the time in development. So the relative time you need to complete a task, depending on the quality of the code. And what we see here is that there's a big difference between the different code quality categories. So if you have green code, you can implement a new feature 10 times faster than, say, your competitors that have red code, right? And this has important implications in the AI age. So first of all, as AI accelerates the creation of new code, we want to make sure that that code is healthy, right? Otherwise, we're just adding to the problem, and our speed up in coding might slow down our comprehension by a factor of 10x, right? But there's another thing to it. What if we rethink AI and apply it to simplify existing code? Because if we can take red code and using AI to turn it green, then we will become 10x faster. So that's what's promising and interesting to me with AI. And of course, optimizing for software maintenance means refactoring. So we're probably all familiar with the process of refactoring. And at the surface, it's a very simple idea. We improve the design of existing code without changing its behavior. But that comes with 2 important implications. First of all, it means that if we change the code and we're not improving the design, then we're not doing refactoring. So that means we need to have some objective way of deciding if one piece of code is better than another. The second implication is that it's also not a refactoring unless we fail to preserve the behavior of the code. Because if we fail to preserve the behavior, then we're introducing a bug. And I think the technical term for violating any of these 2 rules is that we're no longer doing a refactoring, we're doing a refactoring. So for the purpose of this talk, a refactoring is the process of changing existing code while involuntarily altering the program's behavior. Now, based on this idea, we set out to do a deeper study of AI and see if it can help us automate refactoring. And we have published a paper on it called Refactoring versus Refactoring, and you find it online. You will also get the link in this presentation. But what we did to solve the first problem of refactoring, to decide if one piece of code is better than another, was that we needed a benchmarking criteria, and we used the code health metric that you saw earlier. And we used that as a standard to measure, is this piece of code a refactored version? Is it really a refactoring? Is the code objectively better? And I'm not going to go into all the details of how the code quality metric work, but I want to give you a high-level overview so that you know what we're looking at. So the way it works is that code health operates at the file level. So you take a piece of code, and then you analyze it for various code smells, things that make the code harder to understand. And these code smells can come in one of 3 different categories. They can either be at the module level, like class design issues. And to give you just a quick example, things like low cohesion, which means you have stuffed too many business responsibilities into the same module. Now the code is hard to understand because to make sense of it, you need to understand all these different responsibilities, rules, right? Then at the function level, you might want to look for classics like copy-paste logic. That's something that AI assistants are quite prone to introduce. But there could also be other problems like gut functions. So gut functions is something we have all seen. Any non-trivial system contains a few gut functions. So these are typically functions that are very, very large. They are long. And the reason they are so long is because they are low on cohesion. They contain too many responsibilities at the function level. And consequently, they also need to be quite heavy on various conditional logic, right? And they centralize the behavior of the system. So each time you want to modify the code, you end up in the gut function. And over time, they just become more and more complicated. And finally, at the implementation level, we look for various complexity smells, like how is the code implemented? Do you have deep nested logic that doesn't play well with the human brain, or is the code simpler to understand? So we check for these factors and a bunch of others, and then we can categorize every single piece of code as being in one of these 3 different categories. And of course, what we want is our refactorings to come out green. Now, with that said, we designed a study where we asked the AI, or instructed the AI to refactor various pieces of code. And we used this criteria to decide if it was a refactoring or a refactoring. It wasn't a refactoring unless the code health improved. It also wasn't a refactoring unless the automated tests still passed after the code had been refactored. And we didn't write those tests ourselves. We simply restricted the study to code that had a decent test coverage. And in that study, we benchmarked more than 100,000 refactorings of real-world code smells. And that means we could finally answer this question: can an AI help us improve existing code? So let's have a look at what we found. So you see this table here? To the left, you have each AI model that we studied. And I'm going to comment on those because these models are quite old by now. And the first column says valid code. So this is where we simply check, is the code compilable? Is it valid syntax? And we see that the AI does a really, really good job here, right? The AI seems to be optimized for generating valid code. So that's pretty good. The first big drop-off happens in the next column where we say code health improved. So this is where we check, is it a refactoring? Is the code improving in quality? Is it easier to understand? And as we see here, the best performing AI fails to refactor the code in 22% of the cases, and others perform even worse. But the biggest drop-off happens in the last column that says valid refactoring. So this is where we check if the tests still pass. And we see there's a drop-off of like 60-70%, right? And this is quite interesting because imagine you had a colleague, a human colleague, that would break the code in 60-70% of all the commits they were doing. Would you be happy? My guess is that that person would be asked to look for new challenges promptly. But when it comes to AI, this seems to be state of the art, and this seems to be what we accept. I'm going to go back to these numbers soon, but let me first address this question, which I think is very valid. Because the refactoring versus refactoring study was done in early 2024, and since then, large language models, foundation models, they have moved ahead, they have improved significantly. So is it still valid? Unfortunately, it is. And there's another third-party research here that aimed to do something very similar. And this is a brand new study that came out now in 2025. And it still finds that roughly 80% of all attempts from a foundation model, from an LLM to refactor code fail. So we seem to be in the same position now as we were back when we did this study on more primitive and early stage LLMs. So what does this mean? Well, the first time I looked at these numbers, I was a little bit disappointed because I had quite high hopes that AI could help us remediate technical debt. However, my team, they are a team of optimists. They said that this is actually excellent news because a success rate of 37% means that we could successfully eliminate 37% of all the technical debt out there in application code. The only trick is, of course, to be able to identify which refactorings are good and which are bad, right? So with that challenge in mind, we set out to build a solution to classify refactorings in good versus bad. And I want to walk you through the high-level architecture. Then we're going to see a quick demo of how this looks in practice on real-world code bases. But for now, imagine that you as a developer, you write some code. And you see that this code contains one of these code smells that I mentioned before. So you might request a refactoring. But instead of going directly to an LLM, we go to something we call a model selector. So what's the model selector? Well, when we did a refactoring versus refactoring study, we noticed that the LLMs have different capabilities and strengths. Some LLMs are much, much better at certain refactorings than others. So what we did was that we used our research data to train a machine learning model that is capable of selecting the best LLM for the job. So in this case, it might find that depending on what the code looks like, which language it is, it might go to an OpenAI model, or it might select Google or whatever. But the thing is that an AI will always respond. It always gives you a response, no matter if it can or not. So now we know that these responses are likely to be broken in 60 to 70% of the cases. So what we do is that we add a fact-checking layer. So this is where we check, is the code health improving? Is the code likely to be a refactoring? And if it isn't, then we discard the potential solution and we go back and ask another AI for a second attempt. And at some point, we might get a refactoring that's good enough that passes through the validation layer, the fact-checking, and we can now propose that back to the developer as a better way of writing the code. All right, that was the theory and the architecture behind it. Let's see how it looks in the real world. So, for the purpose of this demo, I have picked up a Java codebase. This codebase is called Glovestone. It's a lightweight Minecraft server, so it's a pretty cool domain. And as we see here in the visualization, this is a visualization of the code health in that codebase. We see that there are two large blobs of unhealthy code. So what I want to see is, can we use AI to automatically improve the code health in those parts of the code? So let's start by looking at the code in these unhealthy hotspots. So this is what the code looks like. And trust me on this one, you don't really need a code analysis tool to tell that this code is problematic, right? We can just look at the shape of it. And in fact, this is really just the start of a single function. If I continue to scroll, I see that this is quite a large function. This is what legacy code looks like. And no, we're not done yet. There's more to it. So that was a single function inside a large file containing thousands of lines of code of a similar quality. The question for you is, of course, how long would it take you to refactor this code? Where do we even start? And of course, what could possibly go wrong if we attempt to refactor it? Let's see if an AI can help us. So what we did is that after doing the research, we took our prototype and we turned it into an IDE extension. And the example you see here is from VS Code. So now when I open the code in VS Code, I see that the CodeSyn extension flags this method as being deep nested complexity. That's what we can see. If statements inside if statements, for loops around them, and so on. And what I can do now is that I can click on this code smell. And I see there's a window where I can ask for auto refactor. And if I click on that one, what happens under the hood is that the code goes to a model selector, selects an LLM, gets a response back, validates it, and passes it on to me in the IDE. And I can simply inspect the code and see what it did. So what the AI proposes in this case is quite interesting. The AI identified a large chunk of code. It managed to identify it as a separate responsibility, and it managed to put a descriptive name on it, right? So that allows us to encapsulate and extract this responsibility and simplify the code. That's quite a nice start. But maybe this example was too large. Let me show you a simpler AI refactoring so that we can easier reason about it. So here's another method inside the same class. And I see that in this case, the method is classified as a complex method. So what's that? What's a complex method? A complex method is simply a method that has a high cyclomatic complexity. So that means it has a lot of different branching points, lots of if statements, a lot of loops, a lot of conditional logic. And if I look at this code, I see that, I can kind of understand what it does, but it's not super simple, right? It looks a little bit fragile. So let's see if we can use AI to simplify the structure and reveal its algorithm. So again, I pull it up in my IDE in VS Code, and I click on the complex method smell, and I see that I have the auto refactor option. I click on it, I can diff it, and I can see what the AI did to my code to restructure it. And if I'm happy with it, then again, I can apply it. But before we do that, I want to point out that if you look at in the top right corner, you see this batch, quick inspection. And there's this text that says that this refactoring improves code health and it preserves the semantics of the code. That's really important because this is the outcome of our validation of the fact checking. So I can now be pretty confident that I can apply this refactoring and my code will be in a slightly healthier place. So what this allows us to do using AI together with data and fact checking is that we can move from code to the left to code on the right within seconds. It's really, really quick. And I found that one of the big benefits of using AI is that an AI is really, really good at one thing that we humans are not so good at. An AI is very good at naming things. So if we can use an AI to identify responsibilities and modularize the code, then it very often puts us in a place where we can start to do deeper and more impactful manual refactorings ourselves. And of course, now that you've seen the demo, I hope you're curious to figure out how well does it actually work? Is this an improvement over just using an out-of-the-box LLM or coding assistant? Well, what we did was that after implementing this solution, we benchmarked it. So we reran the refactoring versus refactoring dataset to see how well the fact checking performed. And you see it here in the table. So you see the fact checking contrasted to our raw LLM. And we see that we can elevate the success rate from 33, low 30 percentages to 96, 97, 98% correctness. And of course, a valid question is 98% correctness. What does that even mean? Does it mean that if I do 100 refactorings, I will break the code in 2% of the cases? Yes, that's exactly what it means. However, let me remind you that 98% correctness exceeds the performance of even human experts. So, if we had this magic technology for refactoring code, couldn't we use an AI to kind of rewrite the whole code base, just drop it as an agent and let it refactor all the code? We could, but I advise against it. I think it's important to keep the human in the loop, and I'm going to try to explain why. So, last year, there was a really interesting experiment done by our professor, Professor Klopfer, at MIT. What he did was that he took his students and he split them into two different teams. They were solving the same task, but one group were allowed to use AI, ChatGPT, and other coding assistants, and the other team were only allowed to use old school Googling, right? So they had to figure out answers for themselves. And then he let them loose on the same problem, and the AI team outperformed the other team. They delivered a working solution much, much faster. However, then Klopfer did a really interesting twist. He reversed the tables. So he said that now, please go ahead and solve the same problem again, but this time none of you are allowed to use AI or Google, solve it from memory. And of course, what happened now was that the Google team managed to complete the task, whereas the AI team failed to make any progress at all. And Klopfer made this very interesting observation that working hard and struggling, even if it takes longer, is a very important way of learning. And if you're just given the answer up front, you're not really struggling. Consequently, you're not learning. And as a psychologist, I couldn't agree more with this because it's so fundamental, right? True learning is effortful, and we simply cannot shortcut that. If we do, then we're sacrificing the long-term goal of building understanding and understanding how things work versus the short-term goal of a task completion. So please remember that task completion doesn't necessarily come with true learning nor understanding. And that's really important to keep in the back of our head as we learn about AI. Another thing I kind of came to appreciate over the years is that, yes, we could do lots of automated refactorings, but I think there's so much value of having the human in the loop, because it's really important that we as humans have a mental model of what the code looks like, right? So I think it makes sense to focus on minimal refactorings rather than large sweeping rewrites of the code, because I'm pretty confident that it's all the small stuff that adds up. And I want to remind you all that in the age of AI, acceleration just isn't useful if it's driving your project straight into a brick wall of technical debt. So code quality is more important now than ever before. And the kind of principles I set up for myself to succeed with AI assisted coding are 4 different things. So first of all, I think it's very important that when we embrace AI assisted coding, and it is helpful in a lot of circumstances, then we should also be very clear by setting realistic expectations. That typing faster won't solve our productivity problems. That's simply not where the bottleneck is. The bottleneck is in understanding. And as we accelerate the pace of coding, it also means that code quality is more important than ever before. So we need to enforce a minimum bar for both humans and machines. It's going to be absolutely fundamental. And that also means we need to shift our focus and spend more time inspecting code to build up a mental model, right? And that means we need to acknowledge the rising importance of understanding code over merely writing it. And if I should summarize it all in one sentence, it is this recommendation: that never, ever accept AI-generated code that you don't fully understand. And remember that a healthy code base is the real amplifier, right? Ensure that your AI generates healthy code and value that. So I've come to the end of the presentation, and I want to leave you with a few resources if you want to read up more on this. So to the left, I have a link to the original Copilot study. There were also a couple of resources that I mentioned throughout the presentation. And the Code Red paper might be interesting for you. That's the study where we correlated code quality to business outcomes, faster or better. And you, of course, have the refactoring versus refactoring study. The tool I used for doing the research is CodeSyn, which is my startup. And in case you want to try the AI-assisted refactorings yourself, then please have a look at the ID extension. There's a free version out of it at the Visual Studio Marketplace. And with that said, I want to thank you all for listening to me, and may the code be with you. Thank you.